Hello, today what we'll be doing is we'll be taking up Mobius assignment 5. So let's get started. So our first question is, given that f1 is equal to 10 and f prime at x is greater than 9 on 1 to 5, which of the following are possible values for f at 5? So what this is using the mean value theorem. And what the mean value theorem states is that if f prime at c is equal to f a minus fb over a minus b. And another way to think of it more intuitively is what that equation is saying is that if we have a graph right over here, and if we have a point A and a point B, let's say that there's a function there, put it in purple, so here's our function, that somewhere on this function, the slope of some point on this function, let's say point C, will be the same as the slope between A and B. So if we just put the slope between A and B, or the secant, you can say, between A and B, at some point from A to B, the slope will be the same, like this. Or more exact, it will be parallel to AB. Okay, so let's see what that actually means when we're trying to solve the question. So here, what do we have? We have F1, and we know we're going from F1 to F5. So we're going from F1 to F5. So we can say that FB, just so it's not negative, we can go FB minus FA over B minus A is equal to F prime at C. I know I just wrote the same thing, but now we can start trying to plug in values. So if we say F prime at, so F prime at C, we know that F prime at X has to be greater or equal to 9. So we can say, we can say that FB minus FA, so FA is F at 1, so it'd be 10, something minus 10, over 5 minus 1. That would be our point B and our point A. I'm just going to write it here. So we're going to have FB minus 10 over, we know that it ends on 5, so it's going to be 5 minus 1 should be greater or equal to 9. And the reason it's 9 is because it's f prime. And so we know that f prime at C has to be greater or equal to 9. And again, why? Because we know that somewhere on the graph, it should equal to that prime. So if it's 8, we know that because f prime at x is always greater than 9, we know it can't be 8. So now what we can do is we can sign what f of b, but it has to be minimal. So if we just simplify this, I'm just going to write it over here. So fb minus 10 over 4 is greater or equal to 9. fb minus 10 is greater or equal than 36. fb has to be greater or equal to 46. And this makes sense because let's say we do plug in 46. We're going to 46 minus 10 over 5 minus 1. We'll see that it does in fact is in fact greater or equal to 9. But if we put anything smaller than 46, so for instance, if we have, let's put 42. So if we have 42 minus 6, minus not 6, that's 10. I have really good handwriting now. 42 minus 10 over 4. We're going to get, what is it? We're going to get it's 32. So it's 32 over 4, and that's going to equal to 8, and 8 is smaller than 9. So again, because we know that on f of x, the prime of f of x is always greater than 9, we know it can't be 8. Because it always has to be, it's going to be 9 or greater, because it has to be equal to that. So now that we know it has to be greater than 46, we know it's 46, greater or equal to 46, 47, and 460, because that would match up. Okay, great. Let's click next. So, clear all drawings. So here, what we have is let f of x equal to root of x. Suppose that linearization is to be used to estimate the value square root of 12. Determine the the values of x for which the absolute difference between root 12 and the linearization L at x equals 9 is to within 1/10. So what does this mean? Let's just quickly begin by quickly reviewing what linearization is. So linearization is if I take some function right over here, if I take some point here, what I'm going to do is from that point, I'm going to create a line. So let's put the line green. So I'm going to create a line just like this. And so this line, what it's going to be able to do is it's going to, if you're close enough to the function, it's going to be able to predict the values near it, because we know that at this exact point, the slope is equal to it, and so near it, the slope should be quite close to it. So what this is basically asking is if we make a linearization at 9, at Lx equals 9, then how close can we get away from it so that if we're trying to estimate root of 12, it's within 1/10 of it. And now, just quickly, how do we get the linearization? So again, we know that at this point, let's call this point A. At point A, we know that L at A, which is the linearization, so a point on this line, which happens at A, should equal to F at A, and then the slope of this line, so L prime at A, should equal to F prime at A. So then if we actually build the line, what we're going to get is that line L of x, of f of x, is going to equal to, if we want to build the equation of this line, it's going to have, you can think of it as L of x is equal to f of a, and this is its y. So if we think of it as the equation of a line as y minus y null equals to the slope of the line plus x minus x null. And so y is going to be our function. That's how we have f at a. Or it's better to put f at x because we're not looking at a particular point. So we'll quickly change that. So I'll quickly change that. So it's going to be f at x. Then the slope will be, so it's plus f prime at x, which is the slope, x minus x. And so over here, all these x's are going to be a, because at a particular point, you're going to have your y being equal to f of a. So L prime a is equal to f at a. So that's your y if we actually plug it in, plus the slope. So it's going to be f prime at a times x minus a. So that's what we're going to do here. We're basically going to use this to figure this out. So first we need to find L of x. So to do that, first we're going to define the derivative of root of x. So root of x. So if f prime at f at x is equal to root of x, then f prime at x is equal to 1 over 2 root x. So it's going to be our derivative. So then we can get the equation of the line, L of x is equal to f prime at x. So it's going to be f at x plus 1 over 2 root x times x minus, like, where did it happen? So you can say x minus a. Okay, so now we can just plug in all our values. It's better to actually put a here because you're making it at a particular point. That's why it's always going to be a. Let me erase this. And over here, it should have been a as well. But the equation of the line is that. So the equation of the line, I don't know why I put prime there. Let me rewrite everything. The equation of the line, L of x is going to equal to f at a, the point that you decide to make your linearization from, plus f prime at a times x minus a. So in our case, it's going to be f at a. Our a is 9. So f prime at x when it is equal to 9, it's going to be 3. So we're going to L at x is equal to 3 plus f prime at a. So f prime is 1 over 2 root x. So it's going to be 1 over 6 times x minus 9. And then what we can do is we can just simplify this. So L at x, I don't know why I put prime there. It's really weird. It shouldn't be there. That's not what I meant to say. It's just L of x. So then L at x is equal to 3 plus x over 6 minus 9 over 6, and then 3 minus 9 over 6. 3 minus 9 over 6 is equal to 3 over 2. So then we're going to get equals to x over 6 plus 3 over 2. Plus 3 over 2. Perfect. So now we have our L of x. So now we can calculate how what x has to equal to, basically, so that it does stay within that 1/10 range. So that's what we're going to do. We're going to go x over 6 plus 3 over 2 minus root of 12. Absolute value of that should be less than 1 over 10. Then we're just going to open up the absolute value by placing the 1/10 on both sides. So it's going to be bigger than negative 1 over 10. X over 6 plus 3 over 2 minus root 12, but is bigger than 1 over 10. I'm going to multiply everything by 6. So we're going to get negative 6 over 10, which is equal to 3 over 5. Negative 3 over 5 is bigger, or not, this is bigger, so x plus, so it's going to be 9 minus 6 root 12, but is smaller than 3 over 5. Then I'm just going to bring everything, so it's going to be negative 3 over 5 minus 9 plus 6 root 12. X is going to be bigger than that, but it's going to be smaller than 3 over 5 minus 9 plus 6 root 12. So now if I actually calculate those values, it's going to be equal to that is going to be equal to 11.18, 11.18. So x is bigger than 11.18, but smaller than 12.38. So then we can look at what fits those criteria, that it's in between 11.18, bigger than 11.18, but smaller than 12.38, and none of these work. And just again to kind of show you what this means, and that means that if we draw our graph right here, and then we draw our square root function, and we draw our square root function, and we pick the point 9, so x equals 9. So 9 should be somewhere over here, let's say. So 9, and this is 3. So if we build the line at that point, that's a terrible line. Let's draw like this. So if we build that line, which is tangent to that point, then if we want to be 1/10 within the root of 12, so if we want to be 1/10 within a root of 12, so 12 is somewhere over here, let's say, or x has to be equal. So if we want this line to be within 1/10 of 12, it has to be bigger than 11.18, but smaller than 12.38. So if we plug in 11.18, a number between 11.18 and 12.33 into our linearization equation, then you're going to get within 1/10 of root of 12. Okay, so again, none of the above here because none of it fits our criteria, and then we're going to move on to the next question. So which of the following statements are true about the linearization f at x equals a, denoted by LAX? So this makes no sense. This is just mumbo jumbo. Then this over here, LAX prime equals to f prime at a. What this says is basically that the slope of the line is equal to the slope of the thing at that point. So this session is probably going to cut out because we don't have a lot of time left, but that's okay. So this one would be correct. For all linear functions f at x, LA at x is equal to f of x. That is also true because if you, no matter where you build your line from a line, you're still going to get a line. And then this one's also true because that's like your definition of the line, that your line passes through that function somewhere. that the line at that point is going to equal to the point of that function. So those three should be correct. Hopefully it makes sense why. Next. So which of the following are true statements? If f has a local maximum or minimum at C, then f prime at C is equal to 0. This is not true because if, for instance, we have something like this at A and B, A, then over here, you don't actually have, your derivative here does not exist, but it's still a local max, and this is still a local min, so that's why this is not true. Then if f has an absolute maximum at C, then f prime at C is equal to 0, and that's not true because, for instance, if we take x cubed, f at x equals to x cubed, then the derivative of that is equal to 3x squared, and so at 0, we're saying that, so this one doesn't work just because of the same reasons that we had above. But if you have f prime at 0, it doesn't necessarily mean you have a local min or max, because if we just take x cubed, for instance, then our x cubed functions with something like this. And at 0, even though f prime at c equals 0, it's actually just an inflection point. So if f is continuous on AB, then there exists numbers C and D both in AB such that, so this is not true because it's not a closed interval. Here, because if it was a closed interval, this would be true, but because it's an open interval, you're going to get the function approaching A, but not actually being there. So if f prime at C equals 0, then f has a local minimum maximum at C, and so that's right over here, so that's why this isn't true. So none of the above here. So for this one, what we just want to do is we want to plug in our values and just see if it's an indeterminate form. There are many indeterminate forms. We can think of it, I like to think of it as if there's a contradiction. It's a really good way of thinking of this. For instance, if you have 0 to the power of 0, there's a contradiction here. Because 0 to the power of anything usually equals to 0. But anything to the power of 0 usually equals 1. So if you get 0 to the power of 0, it's kind of a, I don't know what's happening. You can think of all of them like that. So let's start. So cos of x at pi over 2. So cos at 90 is 0. And then 1 minus sine at 90 is 1. So we're going to get 0 over 0. So this would be, in fact, an indeterminate case. Here we have x to the power of 1 over 1 minus x. So we're going to get 1 to the power of 1 over 1 minus 1, which is going to equal to 1 to the power of infinity. And this is also an indeterminate case because 1 to the power of anything always equals to 1, but then anything to the power of infinity is always equal to infinity. And that's where your contradiction comes in. So this is there. So then you have 16 minus 16 over 4 minus 4 is equal to 0 over 0, indeterminate case. Then cos x over x, so cos at 0 is 1, and then x at 0 is 0. So this is not an indeterminate case. So let's punch those in. 1, 2, 3. And click next. Which of the following functions have two critical numbers? So for this one, you just have to take the derivative and then think about it. So if we start with this one, we're going to get, if we take the derivative of this, we're going to get 3x squared plus 10x plus 5. And then we can try to draw this parabola. So this parabola, the way it would look like, I'm just going to go on to Desmos and draw it because I'm sure we can all draw parabolas. Desmos calculator, so it was 3x squared plus 10x plus 5. And so here we see that it goes below. So this would in fact have two critical points. X minus 2 sine x. So if we take the derivative, so we're not going to be able to finish this, guys. I'm sorry I started a bit late, but yeah, hopefully the amount that I did take up helped you. But let's just continue. So x minus 2 sine x. If we take the derivative of that, we're going to get 1 minus 2 cos x. And so this would only yield you, this would yield you an infinite amount of actual critical numbers, because as we know, cos x goes like this, and 2 cos x can equal, so 1 equals 2 cos x. It's a 0, so maybe I can just continue the assignment, but I won't be able to submit. We'll see. So 1 equals to 2 cos x, and so if 1 is equal to 2 cos x is equal to 1/2, and we know that x can equal to a half an infinite amount of times. So this would actually have an infinite amount of critical numbers. So this one doesn't work. So then ln absolute value of x over x. This is quite a difficult case, I can agree. And it is quite hard to visualize it. So you have to draw it very carefully when you are drawing or thinking about it. So ln of x looks something like this, where as you're approaching 0, you approach infinity. Negative infinity, to be precise. So absolute value of that would look something like this, I guess. So ln of x, this. Oh, no, I'm sorry. This would actually look, so absolute value of ln of x. That means that you can also have your negative values inputted. And so that would just look like this. There you go. It would be able to approach it from both sides. And because you're dividing it by x, I think it's actually going to look something like dividing it by x. What's it going to do? Dividing it by x is going to bring it up, I think. So you can check this on Desmos. Ln absolute of absolute value of x over x. And we need to put brackets around this bracket. There you go. So if we just had ln of x, it looks like this, just as we drew, and then dividing it by x, it's going to go like this, because at negative, it would flip it up, and at positive, it would flip it like this. And so then if we would take its derivative, what we would have to do is we would have to look at kind of both cases. We would have to split it up into x is positive or x is negative, because it would become a piecewise function. So if we were to take it if we would take it as x is positive, so ln of x over x, while x is positive, would yield us the result of, if we take the derivative, it would be ln of x, so 1 over x times x minus 1 times ln of x over x squared, which is going to give you 1 minus ln x over x squared. And so this yields a critical point when x is equal to e. And then we would have, when it's negative, it would become negative. It would be the same thing, but just negative, actually. So let's do it. So we have negative ln x of x. And if we're taking the derivative of this, the negative would go outside. So we would end up having happening is that would just be negative 1 minus ln x over x. And so what you see is that negative e would basically work as well. E and negative e would work. So if we actually drew it out, we drew out the derivative, you would see that you would get a couple of those critical points. So let's say that this is f at x equals to this, f prime at x equals to this. And so we see we have one critical number, two critical number, and then the asymptote right over here. And this would not be considered, even though it does not exist, it would not be considered a critical number, because on our graph, on 0, the function doesn't exist. And so in that case, it's not a critical number. For it to be a critical number and it does not exist, it has to exist on the graph. So it's considered a critical number if at 0, the function exists. Then if the derivative doesn't exist at that point at 0, then it would be considered a critical number. So this one does have two critical numbers. Finally, we have 2x to the power of 1/3 minus 4x. So here, if we take the derivative of that, we would get 2 over 3 x to the power of negative 2 over 3 minus 4. And we see that here you will only get one instance of a critical number, because this would only equal to 0 at 1 point, I believe. Let's draw it out before we run to our conclusion. So what would this look like? It would look like 2/3 times 1 over root cube x squared minus 4. So equals 2 So this would only yield 1x, I believe. 1, 0, 1 critical number. Because if you put that to 0, so 2/3 times 1 over 3x squared minus 4. So if you put it on the other side, equals to 4. 1 over root 3x squared equals to, so 12 over 2 is 6. So then we're just going to 1 over 6 is equal to root 3 squared, 1 over 36. And it's going to be cube root of that is equal to x. There's only one case for that. So that's why you would only get 1, 0. And we can check that using decimals again. So g of x equals to x to the power of 1/3. It was 2x. It was 2x 1/3. 2x 1/3 minus 4x. So there it is. So right here it wouldn't exist. Right. So g prime at g prime of x. So I was actually wrong. There are 2 critical points. The reason I got mistaken is because I forgot about the square. The square would make it so that you can have it both be positive and negative. But then over here, the function, and it would actually have 3 critical points because as you see here, the function does exist at 0. And because of that, when the function doesn't exist on the, what is it called? The derivative, because it exists on the actual function, this does not exist actually counts as a critical point. So then we would have 3 critical points and it wouldn't play it in. So just be careful. And I should be careful too, because I mistook when I was taking derivative here. Okay, next. Oh, yeah, so I can't do anything more. So hopefully that helps. And if you have questions about the other ones, just, I guess, put them in the comments and I'll try to answer. Have a good weekend, guys. Have fun. Good luck studying.